Welcome to Chapter 3 of our curriculum. I'm Dr. Ala Jabbar Al-Maliki, and today we are laying the academic foundation for how we secure digital communication. At its core, cryptography is the science of information protection. It is the mathematical process of taking readable data, or plain text, and converting it into unreadable ciphertext to prevent unauthorized access. The discipline is actually divided into two opposing forces. Cryptography concerns the design and construction of secure systems. On the other side is cryptanalysis, the practice of analyzing and mathematically breaking those very same systems. Attackers rely on cryptanalysis to exploit weaknesses. They use methods ranging from simple brute force attacks, where every possible key combination is tested, to complex known plaintext and chosen ciphertext attacks, which analyze patterns between the input and output data. To withstand these attacks, any cryptographic system must achieve a triad of specific goals. It must guarantee the confidentiality of the data, maintain the structural integrity of that data, and definitively authenticate the identities of the users operating in an untrusted digital environment. Early historical methods, like the simple substitution of letters in a Caesar cipher, relied on secrecy of the method itself. Modern cryptography has completely replaced this with complex mathematical algorithms, where security relies entirely on the secrecy of a key, not the algorithm. Today, open, heavily scrutinized algorithms like the Advanced Encryption Standard, AES, and RSA form the absolute bedrock of modern computing security. There is no single cryptographic tool that solves every security problem. Instead, cryptography provides a suite of specific architectural primitives, each designed for a highly specialized task. Building a secure system requires integrating three distinct cryptographic models: symmetric cryptography, asymmetric cryptography, and hash functions. Understanding modern cybersecurity means understanding the engineering trade-offs among these three primitives and knowing exactly when and where to deploy them. We start with symmetric key cryptography. As this diagram illustrates, symmetric systems use a single shared key for both the encryption and decryption processes. Algorithms like AES and DNES utilize this model because of one primary engineering advantage: they are exceptionally fast and computationally efficient. That low computational overhead makes symmetric algorithms the industry standard for encrypting massive local databases or processing continuous, heavy streams of data. However, applying this architecture across an open network reveals a critical structural flaw. It creates the key distribution problem. For two parties to communicate securely, they first have to share the secret key over a compromised channel. If a malicious actor intercepts that single key during the initial exchange, the entire system fails instantly. The attacker can now read and modify every packet of data. While symmetric encryption is ideal for local processing speed, it is mathematically unviable on its own for strangers attempting to establish a secure connection over the open internet. To solve the key distribution flaw, network architectures employ public key cryptography, also known as asymmetric cryptography. Instead of relying on one shared secret, an asymmetric system generates two mathematically linked keys, a public key and a private key. The public key is strictly used to encrypt data and can be published openly. Once locked, data can only be decrypted by its mathematical pair, the private key, which is never transmitted. Algorithms like RSA effectively solve the distribution problem, but the trade-off is severe. The mathematics involved require massive computational overhead, making asymmetric systems drastically slower than their symmetric counterparts. Asymmetric keys also introduce a second critical capability: digital signatures. By reversing the process and encrypting data with a private key, a sender proves their identity, guaranteeing authentication and non-repudiation. Network designers purposefully sacrifice processing speed in asymmetric systems to achieve trust, verify identity, and safely exchange information across hostile networks. Up to this point, we have discussed encryption, which is designed to be reversed. We now look at a strictly one-way architecture. Hash functions are deterministic algorithms that convert an input of any size into a fixed-length string, known as a hash value. This process relies on the avalanche effect. Altering even a single letter in the input completely randomizes the resulting hash value. A secure hash function operates under strict mathematical requirements. It must execute quickly, and it must be collision-resistant. Collision resistance means it is computationally infeasible to find two different inputs that produce the exact same hash output. Each input must generate a unique digital fingerprint. In computer science, this is how systems handle password storage. Databases do not store plain text passwords, they store the hash value. When you log in, the system hashes your input and compares it to the stored string. Hash architectures mathematically guarantee data integrity and credential safety, precisely because they never reveal the original input. In real-world engineering, these three architectures are never deployed in isolation. They are stacked together to form a highly efficient hybrid cryptographic engine. The standard web browsing experience, the HTTPS protocol, demonstrates exactly how this synthesis works in practice. Step 1. HTTPS initiates the connection using asymmetric encryption, typically RSA. Because it is slow, the system uses RSA just long enough to authenticate the server's identity and securely exchange a temporary symmetric key. Step 2. With the keys safely distributed, the system abandons the slow asymmetric process. It immediately switches to symmetric encryption, like AES, using that temporary key to encrypt the bulk web traffic at high speeds. Step 3. Hash functions like SHA-256 operate simultaneously in the background. They verify the digital certificates and check every data packet to ensure nothing has been tampered with during transit. By combining these protocols, absolute trust is mathematically established in milliseconds. The system perfectly balances the speed of symmetric keys, the secure exchange of asymmetric keys, and the integrity of hash algorithms. Cryptography is a dual-use discipline. The mathematics that defend our networks are actively utilized by malicious actors to attack them. Ransomware operators leverage the unbreakable mathematics of symmetric and asymmetric encryption to lock a victim's files, extorting them for the decryption key. Similarly, when massive database leaks occur, they are rarely the result of broken algorithms. They are the result of poor implementation, such as an organization failing to properly hash stored credentials. As Dr. Al-Maliki emphasizes in this curriculum, mastering these architectural primitives is an absolute prerequisite for any career in IT, network design, or cybersecurity. Cryptography provides the structural force that makes zero-trust networks, secure global communication, and the entire modern digital economy possible.